Hello and welcome to this second video on advanced transport phenomena. Today we have temperature and fluid velocity get along very well, or in other words, convective transport. Why is that? Well, first of all, in the last topic we talked about the dimensionless Peclet number for both heat and mass transport, if you remember, and how useful this Peclet number is to determine what the governing mechanism, either diffusion or convection, is in a transport process. So if you remember, when the Peclet number is much larger than 1, that means that the effects of convection are much more significant than the effects of diffusion. If you remember, diffusion applies here to both heat and mass transport when there is a gradient in temperature or concentration, respectively. And this is actually normally the case for any system larger than the millimeter scale. So practically 99% of chemical environmental processes have convection as the most significant or most important transport mechanism. However, please don't forget that because the Peclet number is proportional to the system size, to that characteristic length L, we find that at really small scale, and we're talking about micrometers or below micrometers, the Peclet number is much smaller than 1, and in that case the diffusion contributes much more effectively to both mass and heat transfer. In this topic, what we're going to do is to focus more on convective processes. That means processes in which the Peclet number is much larger than 1. An example of this in the manufacturing industry is, for example, the heat sinks used in electronic structures. So in this case, we're talking about aluminum heat sinks through which we force a cooler airstream to flow across. So these heat sinks can be used to increase the surface area of certain electronic components that need to be cooled down. And by increasing the surface area, we increase, let's say, the effectiveness of the cooling process. So if this can be smartly engineered to occur within a compact volume, the cooling device will also be obviously more efficient. So in this case, we can observe that the thermal energy is transported through diffusion in the aluminum heat sink material, and then obviously through convection into the cooling air. And this, well, the convective cooling effects of this heat transfer process obviously effectively prevent components from overheating or failing. So we have here a convective transport of heat, which helps to kind of preserve the integrity of the structure of the electronic components. Now, I want you to have a look at something really important. This convective heat transfer process will mean that temperature obviously is changing. And this will have an effect on the air velocity, which needs to be considered. Let's have a look at how the velocity is included within the heat conservation equation in the convective term, which is the third term. So that means that velocity and temperatures are coupled variables, so they depend on each other. One will affect the other and vice versa. But before digging deeper into convective processes and how the velocity of a fluid changes the temperature of a fluid system, let's have a short refresher on fluid velocity. How is the velocity calculated at each point within, for example, that system? Is the velocity constant at every single point or not? Well, for engineering design calculations, you can usually assume a constant velocity for example, water flowing inside a pipe or air flowing through a compressor. That's what you usually do when you design a process. However, assuming a constant value is not enough if we are meant to look at the process from a microscopic point of view to properly understand the physics behind transport phenomena. So in the same way that the Newton's second law is used to analyze the movement of solids, if you remember from physics, there is a modified version of this Newton's law, which is for fluids. And in particular, we have 3 equations, the well-known Navier-Stokes equations. So Newton's second law is mass times acceleration is the total force applied over the solid. So we have the same for the Navier-Stokes equations. We have on the left-hand side mass times acceleration, although that it's expressed in terms of mass divided by volume. So that means the density. So the density times the acceleration of the fluid, which is the term into the brackets, equals the total force. So in this case, in a fluid, we have different forces behind the fluid flow, which are the pressure forces, which is represented by that minus gradient of the pressure. We have viscous forces, so that's the third term, viscosity times the Laplacian of the velocity. And then we have gravitational forces, which is the last term in the Navier-Stokes equation. As you can see, density times gravity. So by solving these equations, and again, note that we have to solve 3 equations, one per coordinate direction, because U is a vector, a 3-dimension vector, and therefore we have 3 Navier-Stokes equations. So by solving this Navier-Stokes equation, we get an accurate description of the velocity field across a system. Solving this equation will give you a solution, a numerical solution for the velocity at each single location and at each time within that fluid system. And this velocity field, that U vector, is the responsible for the convective transport of heat and mass. The value of the fluid velocity at each single location will obviously influence the rate of mass or heat transport at that specific location, right? So now let's have a look at what happens when the fluid flows over a stationary surface. For example, a flat plate, or the bed of a river in the case of environmental applications, or for example, in the case of process engineering, over the wall of a pipe. So in this case, the fluid touching the surface is brought to rest by the shear stress at the wall. You know this from fluid mechanics. In other words, the fluid in direct contact with the surface has a 0 velocity. And this is an important concept. This is called the no-slip condition. The velocity of the fluid which is in contact with a surface, with a solid surface, has the velocity of the surface. So obviously, if we're talking about a pipe, the velocity of the wall of the pipe is 0, because the pipe is at rest. So that means that the fluid which is in contact with the wall pipe has 0 velocity. And therefore, as a result, we can see that there is a region in which the flow velocity changes from 0 velocity at the wall up to a maximum value in the mainstream of the flow. And this region in which you have that velocity gradient is known as boundary layer. And the concept of boundary layers is not only important in fluid mechanics, but also in the theory of heat and mass transfer. Why is that? Because we're going to find that we have diffusion of heat and mass across boundary layers, and this diffusion process across the boundary layer will often control the rate of heat and mass transfer operations. So now let's consider the fluid flow over a flat plate, like the one shown in the figure. As you can see, there is a uniform velocity profile. That's U infinity on the left of the figure, and this velocity profile hits the leading edge of the flat plate. And then a laminar boundary layer begins slowly to develop across the distance of the flat plate, which is, this boundary layer is largely affected by the shear stress of the fluid in contact with the wall, or in other words, the boundary layer which begins to develop is largely affected by the viscosity of the fluid. And the flow actually in this region, in the laminar region, is very predictable. Indeed, one could estimate the increase in thickness of such a boundary layer just by solving the Navier-Stokes equation in that region. We're not going to do that, but I can provide you with some resources to see how to solve this complex equation in the laminar boundary layer region. So if you solve that equation, you would get what is called the Blasius solution to the Navier-Stokes equation. And the Blasius solution is that delta. That delta is 5 times x, which is the distance through which the fluid flow through which the fluid flows across the flat plate, divided by the square root of the Reynolds number. And this delta is the thickness of the boundary layer. So we can estimate the thickness of the laminar boundary layer by just knowing the Reynolds number. All right. However, after some distance, you can see that we have small chaotic oscillations that begin to develop in the boundary layer, and the flow begins to transition to turbulence, eventually becoming fully turbulent. And in this case, when you have achieved this turbulent condition, the viscous forces become much less significant than the inertia force, as opposed to the laminar boundary layers. In this case, we have to look for other empirical correlations if we want to compute the value of the thickness of the boundary layer, and that's quite advanced. Now, if we have a look at our convective heat transport problem, similarly, as a velocity boundary layer develops when there is a fluid flow over a surface, a thermal boundary layer must also develop if the bulk temperature of a fluid is different to the surface temperature. So think about a fluid flow over an isothermal plate, like the one in the figure, which is at a constant temperature, T0. So T0 is the temperature of the flat plate of the solid surface. And now, if you have a look at the left, at the leading edge, the temperature profile of the fluid is uniform, and the fluid temperature is T infinity. That's the fluid average temperature. Now, the fluid molecules that come into contact with the plate achieve thermal equilibrium at the wall temperature, and at this point, we have a heat flow taking place at the surface purely by diffusion, or in other words, conduction from the surface into the fluid. And these fluid molecules exchange energy with those in the contiguous fluid layers and so on. And what we have is a developing temperature gradient in the fluid. So we have a temperature gradient from the surface into the mainstream of the fluid. So in this region of the fluid in which we have temperature gradient, that's called the thermal boundary layer. So in the same way as for velocity boundary layer, we can define a thermal boundary layer thickness, delta T, which is the thickness you can see in this figure. And this thickness, the thickness of the thermal boundary layer, will grow with increasing distance from the leading edge of the flat plate. However, it is important to remember that the thickness of the boundary layer is generally different to the thickness of the velocity boundary layer, obviously, because the first deals with temperature gradients, whereas the second one deals with velocity gradients. So the thickness of the velocity boundary layer is usually different to the thickness of the thermal boundary layer. Now, the thickness of the thermal boundary layer, of course, will dictate how efficient the heat transport process will be. Or in other words, the thickness of the boundary layer will dictate the heat flux between the surface and the fluid stream. Obviously, the thicker the boundary layer is, the higher heat transfer resistance we have, and therefore we have a lower heat flux. In this regard, we can compute we can estimate the heat flux in joules per meter square and second between the surface and the fluid, as long as we know the value of such thickness, delta T. Indeed, we can define, and you know this from design, we can define an effective convective heat transfer coefficient, H, which is just the ratio between the thermal conductivity of the fluid, K, and the thickness of the thermal boundary layer, delta T. So you've used in the past this H, heat transfer coefficient, But what you didn't know is that this heat transfer coefficient is just a ratio between the thermal conductivity of the fluid, K, and the thickness of the thermal boundary layer, delta T. That's why it's important to know what the thickness of this boundary layer is. As you know, the effective convective heat transfer coefficient, H, depends on the physical properties of the fluid and the physical situation, let's say the fluid velocity. So the convective heat transfer coefficient is not a property of the fluid. It is usually obtained in an empirical way, conducting different experiments, and the value of H will depend on the variables influencing the convection, surface geometry, nature of the fluid motion, properties of the fluid, bulk fluid velocity. So you will have to use an appropriate empirical correlation to get the value of this H. Now, if you wish to compute the global heat flux in your system, so the total heat flux, which is the total amount of heat which is gained or lost by a fluid system, then you can just compute the heat flux over the whole heat transfer area. So you have JH, which is the convective heat flux, equals, or is roughly equal to an effective heat transfer coefficient H times the area times the temperature difference between the fluid and the surface. Note that we can talk about local or global heat fluxes. A local heat flux will take into account the boundary layer thickness at a specific location. So that means that the effective heat transfer coefficient H changes because the boundary layer thickness is not constant. However, to design heat transfer equipment, we are usually more interested in computing global heat fluxes rather than local. And therefore, to compute global heat fluxes, we use an average heat transfer coefficient from different correlations. Before finishing this video, I want to grab your attention for the last time. Similarly, we can define a concentration boundary layer for mass transport between a fluid and an interface. Indeed, the thickness of the concentration boundary layer will dictate, in this case, the mass flux between the surface and the fluid stream. And obviously, the thicker the concentration boundary layer is, the higher mass transfer resistance, and therefore the lower or the poorer mass flux you will have. If you can compute, obviously, the thickness of this concentration boundary layer, then you will likewise be able to estimate both the local and global mass fluxes. So exactly the same logic applies to mass transport.